Hey guys, in this video I am going to go over the projectile motion a little bit. So we already know about the 1D motion along horizontal direction, and then we also know the 1D motion along the vertical direction. So the projectile motion is a combination of the two. So you can either draw it like in this form where you have 1D or along horizontal and 1D along vertical, and the resultant would be pointed in a direction like in this form. The resultant of these two vectors, and the one along the horizontal direction and the one along vertical direction, that will give you a resultant vector as I am drawing using my white marker pointed in that direction. So for example, if you have an object going in this direction, that will create a projectile path in this form. In the class we discussed a couple of different cases, so I'm not going to go over them again. But something to mention here, we know that our familiar equations, V final, V initial plus AT, one equation, delta x equals V initial t plus 1/2 AT square, and then the last equation, V final square equals V initial square plus 2 times A delta x. So these are the three kinematics equations that we know from before, and we are using these three equations along x direction and along y direction separately. So if you remember from the first section, we used to set up tables, one for x direction and one for y direction, and we usually took the rightward direction for like x as positive and upward direction for y as positive. So we are going to stick to the same, and it is essential that you either you draw the tables or keep track on the two different motions along x and y directions. Now couple of things that I want to mention here. The accelerations. The acceleration along x direction, unless stated otherwise, is 0 meter per second square, and the acceleration along y direction, taking up as our positive direction, and that is negative 9.8, that also is understated otherwise. For example, if you have an object moving with an engine or with an external force, this is not going to be the case. So those are basically considered as specified in other ways, right? So unless stated otherwise, in any form of a kick, or like a basketball throw, for example, a dart going shot from one place and going into another place, and also you can say like a ball rolling off of a table. They are all unless stated otherwise cases. There are no external forces acting on those situations. All right. Now I am going to take a picture from the textbook, and I'm going to discuss one problem, and as we discuss that, couple of important things will be mentioned. Okay, so I copied a problem from the textbook that we are using, and here you can see that a person is throwing a ball 25 meter per second at an angle 40. So these are important things. You can highlight these things as you go, and then just a second, I am going to highlight that. Let's pick a different color. 25, that is the initial velocity, and it is set at an angle of 40 degrees with the horizontal, and there is the range, or the x component displacement is given as 22, and it doesn't say anything like specifically about the acceleration, so this is an understated otherwise case. So let's actually set up the tables. Let's do the white color, and then here you have the x table, and there you have the y table. I have them side by side. Sometimes you can do the problem, depending on the problem, you can do them without using a second table, but just for the safety I am using both. So here you have x and initial x component, final x component, ax, delta x and t. We know one thing, that t is common in both tables. So here's the y-axis and positive along y direction. So here you have VIY, AY, I don't have the same order, but that's okay, VFY and delta y and t. Now the things that we know, AX is 0, AY is negative 9.8. Delta X is given to us as 22, correct SI units, 22 meters. And VIX also, we can take it as 25 cosine 40. And check your calculator, I may have these things wrong, I don't know. I just found it out, 16.06 meter per second. But again, have your calculators in degree mode and then check these things out. And then VFX does not change because there's no acceleration pointed along that direction. So we have it in the same form as that. And then AX, as we said, meter per second square, that we already know. Now the question asks us, the first part of the question asks us, how far above the release point does the ball hit the wall? So if you go down up a little bit, so basically if the trajectory goes along that, and then this is what we are basically looking for. Release point, right? So release point, let me just erase this a little bit, and that's right. And that's what we are looking for, only up to the point over here, up to the point over there, right? Okay, so let's start with what we the table that we have most of the components. By the way, we can fill out VIY as well, and there you have 25 sine 40 actually, you know what, 25 sine 40 is the 16.06. I just checked that, and this is meter per second square, and the cosine term actually is 19.15. again, check it out, 19.15. all right, so X table has a lot of information. So let's start with delta X equation. V initial along x direction times t plus 1/2 ax t square. I don't want to make the videos too long, so you can slow it down, or you can just come back and listen to this. And delta x is given to us at 22. Vix, we have it as 19.15, and using this you can find t, and the t would be 22 divided by 19.15. Okay guys, so you can see that I wrote down the equations for the second part, where you find the height of the wall where the ball hits from the starting point. And the first equation, delta y, v initial y times t, half a yt square, you can follow that. And then I substituted for VIY, and then the time is taken from the previous found time over here. And then 4.9 comes from 1/2 times negative 9.8. So the combination of AY and 1/2 together gives you negative 4.9, and then 1.15, right? Okay, so I am going to do the calculations. Actually, I did the calculations, and there you end up with 11.99 meters. So you can roughly take it as 12 meters, and 12 meter is the height of the wall where the ball hits, or the point where the ball hits, because it asks how far above the release point does the ball hit the wall. So this is the part that we were looking at on the picture. And then the second part asks us what are the horizontal and vertical components of its velocity as it hits the wall. Now we already know that the horizontal component, the velocity, does not change. So conveniently we can write the answer for B. V final x equals to 19.15 meter per second, because AX is 0, velocity does not change, sort of like the cruise control on your car. When you are on cruise control, you do not apply an acceleration and the car maintains the constant velocity. But for part C, where it asks V final y, where you have to use the equation V initial y plus AY t. And then V final y, I'm just going to show you the substitution. Then I'm using my calculator separate and plug the numbers in. 9.8, 1.15, and do the math. You will get V final y component equals to 4.79 meter per second, and that is the answer for part C. Here's the answer for part B. Now if I draw the picture here onto the side, that's what you will have. Here is the point that the ball strikes the wall, and at that point the y component velocity is 4.79 meter per second. X component velocity did not change at all, and it stays as 19.15 meter per second. So this is the picture, like, you know, if I draw the projectile, the path as well as the moment that it hits the wall, and this is where the ball is released, and it is of course not from the ground because the man has some height, and then this part is not taken into consideration. The height of the man part, that was not taken into consideration. Delta y is already found as 12 meters, right? And then the next part asks us, the last part, when it hits, has it passed the highest point on the trajectory? Now we already know the highest point on the trajectory, the information about the highest point on a trajectory. So let me draw the full trajectory and just draw that like that, and let's mark the highest point. Now if I ask you to draw the velocity components at the highest point, since we are almost actually done with the chapter, you should be drawing only the x component of the velocity. What happened to the y component velocity? Well, y component velocity at the maximum is 0. Right after this point A, the y component velocity direction switches, and now it is pointed in the negative direction, but of course the arrow size grows up. Now it's the same coming up, the arrow size went down, like indicating that the velocity is going down. At point A, velocity is 0, and thereafter the arrow points in the negative direction, showing that there's a negative velocity. So clearly the one that we found over here in part A, under part C, y component velocity is still positive. It is of course smaller than the original initial value, but it is still positive. So that tells us that we are somewhere like over here. And now I can draw the wall at this point. So you can clearly say, by looking at, we did not do any calculations, we simply looked at the picture, we observed the final velocity value along y direction, and we have a positive value. So we say, all right, so we still are ascending, not descending. Okay, so we can say that as the answer to part D, we can say that the ball has not passed the highest point on its trajectory. The ball, I'm going to write script letters so that you won't hear that annoying sound. The ball has not reached the max. The ball has not reached the max, and that's the answer.